Hi everyone, my name is Yusheng Zheng. I'm the founder of the Eunomia BPF. Today, I'm excited to share our project, Code Survey, which uses large language models to help us understand large code bases. First, I will start by talking about what actually means to understand code bases. We know that language model can help us understand code, which understand very often struggle when comes to answer questions about really big code repos like Linux kernel. Today, I will go over another approach to explore Git repos or big code bases, and I will show an example of how we try to gain insights from eBPF in the Linux kernel. And I will also discuss some best practices we've learned and our next steps. First, we all know that LLMs can help us find bugs and write code, so I do understand code to a certain degree. But understand code isn't just about fixing bugs or writing functions. Sometimes we are trying to answer more high-level questions about the code and how it evolves. For example, we might want to know how new features impact stability or performance, or where they are stages in a component's life cycle. We may ask how certain features have changed over time, which parts of the code are most likely to have bugs, or how different features and components depending on each other. These high-level questions can help us with things like software design, bug studies, find root causes of issues, improve code review process, and make software more stable. They can also help us design new debugging tools or CI tools, or make it easier for newcomers to understand open source projects. So why are we using large language models for this? Traditional methods are limited. Data analysis and manual code review are very time consuming, and even less. They often don't tell a full story. There are so many insights hidden in commits, emails, and other kind of unstructured data. This data produced during the software development could be really valuable, but if we only rely on traditional methods, they are often limited by things like bias and subjectivity. If we just try to apply large language models into these use cases, they also face their own trends when it comes to understand large code bases. For example, within context learning, we can put snippets of code into the model's context, but this has strict limits due to the context length. We can't load the entire Git repo into it. There's another approach called RAG, when we combine language models with internal sources of knowledge by smoothly rely on accurate retrieval information. So it's really only good on small, precise questions about specific code snippets. Anthony is another option where we adapt models with specific data, but it's costly, time-consuming, and there's a risk it might get too narrow and miss the big picture. These approaches are generally not eager for answering high-level design questions like span multiple hours or across all the build report, and even more, it may have a long history during the report development. That's why we are proposing a new approach we call Code Survey. Code Survey is the LLM-driven methodology or tool for analyzing code bases or Git repos. The basic idea to think about how we measure is that what if we could ask every developer to take a survey about everything in configure during the development process? So the idea is we can treat large language models as if they were human participants in a survey, because in a way, software development is a social activity. Using this approach, we can take everything involved in software development, commits, emails, discussions, and turn it into a structured dataset. Then we can run queries, perform quantitative analysis on development process, and visualize the results. Here is how Code Survey works. First, we have experts and LLM agents working together to come up with high-level questions. These questions can help us figure out what we need to know. Then we identify the required data types and source to answer these questions. After that, we design survey questions based on the data we've collected. The LLMs then use these questions to process the data and answer the survey. After this, we either have human experts or more LLM agents evaluate survey results to make sure they are accurate. If needed, we refine the questions or the survey process based on the feedback. Finally, we end up with a dataset that's tagged and organized, allowing us to analyze the data in a structured way. For example, we create a survey definitions about classified commits. We might ask, which the main type of this commit with several choices like bug fix or new features, and so on. We also provide some context for a survey so a language model understands the background. It's like a description and hint. These survey definitions are then turned into prompts, like this one, which include the commit details, description, and the question we ask. With this prompt, we can process thousands of commits to generate a meaningful data set, or even hundreds of thousands commits. Now let's look at our case study on the eBPF subsystem in the Linux kernel. eBPF is a subsystem that allows you to run programs in the kernel. It's like having a virtual machine in the kernel. So why do we pick eBPF? First, because we know a lot about it, which means we can ask kernel experts to confirm our findings, because our company or organization are mainly doing eBPF ourselves. Second, eBPF is also a rapid involved subsystem with a lot of complexity and functionality. We apply code survey to analyze the evolution of eBPF to get insights that we were interested in. Initial results. We observe, for example, we observe feature changes over time since eBPF is event-driven. It can attach to multiple events like network events, tracing events, profiling events, or security hooks. We could see how these events has changed over time, which reflects the evolving use cases for eBPF. Initially, eBPF was designed for network-related features, but now it has expanded to include more features like GitOps or security control. You can see that in the features. We also look into the interdependency between features and components. For example, where new features add, which components need to be modified. We found that the SQL interface and the libBPF library are closely related. Some features require changes to both of these. Helpers and kernel functions are also tightly coupled with the eBPF verifier. Adding new helpers or keyfunds usually involves updating the eBPF verifier to add more logics. When we add runtime features in eBPF, like a BPF link, tokens, or BPF ether, this often need to update to multiple components at the same time. For example, we also found that adding new eBPF instructions often introduce more types of bugs in the eBPF verifier. In this feature, we compare the total numbers of bugs in the verifier with the addition of new instruction features, and there's a clear overlap between them. If you are interested in a more detailed report, it's available on GitHub and our archive paper. Now, let's talk about some best practice we've learned. Using predefined tags or categories can help us standardize their response, which then make the response clear and reduce ambiguity. Implement workflows for LLM agents to review and refine their answer, which improves accuracy. We also know the models to allow the models to answer. I'm not sure if they don't have enough information, which prevent them from giving misleading answers or hallucination. We start with parallel testing and refine our survey iteratively. Make sure the questions are clear and logically consistent. Finally, we make sure to validate the data for consistency and catch any contradictory answers. This approach helps us improve the readability and accuracy of the data generated by LLMs. It can also apply to other, not just code survey, like other tagging or text. However, code survey also has some limitations. For example, LLMs can make mistakes, so they may sometimes misinterpreting information or hallucination by providing incorrect answers. Human experts is still sometimes needed to help with the desired survey questions and validate results. Also, the quality of the results depending on the data. If the data is incomplete or there aren't enough resources, it can leave gaps in our understanding. For next step, we plan to automate the process even more so that it requires less human effort. We are working on making it decentralized and scalable. And we are also refining the process using more advanced LLMs to boost efficiency. And another priority is like to building a robust framework for evaluation, which makes the validation more reliable. And finally, we are planning to apply the code survey to other projects like LLM, and Kubernetes to see how well it's class. Thanks for your listening. You can find our Git repo and the archive paper and these links.